Hello everyone. Today I'm going to talk about our paper to DCASE 2021. The name is a Contrastive Semi-Supervised Learning Framework for Anomaly Sound Detection. I'm Xinyu from Tsinghua University. At the beginning, let's go through the outline of this presentation. I will give the introduction at first about the problem definition and the mainstream methods. Then I'm going to talk about our proposed semi-supervised learning framework and data augmentation techniques. Finally, I'm going to talk about our experimental results. Anomaly sound detection is the task of identifying whether the sound emitted from an object is normal or anomalous. It has a wide range of applications, such as machine condition monitoring and home monitoring. In this paper, we focus on anomaly sound detection in an unsupervised setting, which means that only normal sound samples can be accessed during the training phase. There are two mainstream deep learning-based methods in DCASE challenge: unsupervised autoencoder-based model and supervised CNN-based model. The main idea of an unsupervised model is to learn the inherent consistency of the normal sounds and then classify samples as anomalous or normal by the deviation of a sample from normal sound properties. Recently, in the DCASE challenges, supervised training is made possible since the challenge training data is composed of normal sounds from different operating conditions with different section IDs. CNN-based ASD method uses the section ID as a label and then performs classification on latent features. As we can see from previous works, for deep learning-based anomaly sound detection methods, a key issue to improve the performance is to obtain better latent space features of normal sounds, both for the widely used autoencoder method and the classifier-based method. Inspired by the recent success of contrastive learning approaches for self-supervised audio pre-training, we aim to enhance the model's capability to detect unseen events by linking multiple views together. As shown in the picture on the right, our proposed learning framework is a novel combination of two mainstream anomaly detection models trained with an additional contrastive loss function. First, we get the output vector of autoencoder's bottleneck layer and the CNN's feature layer. Then we transform them to the same dimension and map vectors to the space where the contrastive loss is applied via a shared MLP projection layer with one hidden layer. In addition, we use some data augmentation techniques for this task, such as mix-up, time masking, and frame shifting. Besides conventional techniques, we use the median filter to suppress short-term noise. As shown on the left, the original spectrogram contains a lot of short-term noise. After median filtering, these noises are suppressed. We use DCASE 2021 official baseline systems for experiments. As it can be seen, our MobileNet V2 model trained in the proposed training framework shows improvement over the baseline model in some machine types, such as fan and sliders. For the DCASE challenge, we trained an EfficientNet B0 based model under our proposed training framework, along with media filter and other data augmentation techniques. For the challenge, our method ranked 9th out of 27 participated methods. It is worth mentioning that the table on the right shows that our method performed best on the fan dataset, especially from the perspective of partial AUC metric, leading by a large margin of around 9% compared to the second result. We believe that it mainly contributes to the media filter applied on the log-mail spectrogram along the time axis, since it can erase short-term noise and improve the generalization ability of the model. Thank you very much for watching this video.